Hi, my name's Dr. Adam Booth, and I'm Associate Professor of Applied Geophysics in the School of Earth and Environment at the University of Leeds in the UK. First of all, thanks very much to the organisers for inviting this talk and also for allowing it to be presented in a pre-recorded format. Sorry that I can't be there to present and discuss it live, but it is 2 AM in the UK and I assure you that I am asleep. But I'm dreaming of distributed acoustic sensing, and particularly an experiment that we were able to do in summer 2019, the first of its kind, where a length of fiber optic cable was installed in an ice borehole, and we were able to do some distributed acoustic sensing there. It was a really interesting data set, loads of really cool insight about the seismic structure of this particular glacier, but with the benefit of hindsight, maybe there's more that we could have done to enable the accurate representation of the frequency content in our data. So my talk is a curious case of frequency content, gauge length lessons from borehole DAS in ice. What I'll do in this talk is give you a quick crash course in the seismic structure of glaciers, why we're interested in it. I'll show you some of the data and then show you some of the limitations of our experiment. So what you're looking at here is a map of Greenland. The orange square shows our study glacier. It's called Store Glacier. It's a major outlet of the Greenland ice sheet. It flows at something like 500 meters per year and discharges icebergs into Baffin Bay. Now, if we're going to predict how this glacier might evolve in a warming climate, this is where seismic measurement comes in. Seismic properties sense the mechanical properties of the ice, which can be really important to feed into dynamic ice flow models. So, what do those seismic properties look like? Here's a schematic cross-section through a glacier. You've got some thickness of ice, in our case it's around 1 kilometre, overlying some deformable sediment layers and eventually underlying bedrock. We're interested in the ice and the sediment layers. The sediment layers dynamically evolve in terms of their hydrology, and the interaction of the ice and that hydrological system is a real big control on ice movement. What we normally expect for ice itself, though, is that for the majority of the glacier it will be isotropic, p-wave velocity of something like 3,750 meters per second. At some point we might have a flow fabric that develops, so all of the ice flow causes all of the ice crystals to align, and the fast axis of an ice crystal, it gets orientated vertically. So at this point a vertical p-wave might be propagating at over 4,000 meters per second. Go deeper into the glacier and eventually you'll get into what we call temperate or warm ice. It's where the ice is at its pressure melting point, so there is intracrystalline water, liquid water, between the crystals of ice there. So we might expect p-wave velocities to reduce. We'll come along with a seismic reflection survey. We measure reflected travel times, we can build up a velocity model, we can measure the reflection coefficient at the base of the ice and say something meaningful about the sediment properties, and we can also measure the attenuation rate of the seismic energy. This has been shown to relate to ice temperature and is an important thing to bear in mind when it comes to thinking about the mechanical deformation of the ice. Now, other experiments I've done around Greenland suggest that Q in ice in this area is something like 300. So we were able to do a DAS experiment on Store Glacier to see if the borehole insight would allow us any better constraint of all of these different seismic properties. So here's a quick view of operations on Store Glacier. What you can see in the main picture is our drilling equipment. We drill a vertical borehole using hot water methods. So water is pumped from nearby meltwater streams into a heating and pressurizing system. The water is pumped through the hose over the top of the drill tower, and that pressurized and hot water is used to melt and blast a vertical borehole, probably on the order of 10 centimeters across. When we reach the glacier bed at 1,043 meters, we then install fiber optic cable. Initially, that borehole is full of liquid water, but then over the course of the next day, that water freezes and the cable becomes very, very well coupled to the surrounding ice. We then measure distributed acoustic sensing using a Silixa IDAS system with a 10-meter gauge length, and the seismic energy that we're recording is basically me hitting the surface of the glacier with a 14-pound sledgehammer. We have various shot locations around the borehole. Each of them is something like the sum of 35 individual shots. Here's the distribution of all our shot locations around the borehole. You've got the borehole there in orange. We did lots of zero offset shots just here, but then there's also a lot of walk around and walk away shots to something like an offset of 500 meters from the borehole. Now I'm only going to show you the zero offset shot in this particular presentation, but there's a paper out there in Geophysical Research Letters. If you type those search terms into your search engine of choice, then you will find the paper and you can see some insight from some of the offset shots as well. So here is an example of a zero offset VSP record. It's pretty nice, really pretty clean. Our hammer shots go down the full length of the cable, and also in some other shots you can see you get reflections coming back up. So we were really pleased with the general data quality, the detectability of the seismic energy. It all looked very promising. What I did here was to show some frequency content in the data, which I'll come back to in just a second, but I'll first just do the diagnostic anatomy of this VSP. What I think we've got is the direct P wave there marked in red. There is also some scattered P waves arriving, which I think are coming in from nearby crevasses. If you get your eye in closely, you can maybe see that there's a tube wave coming down. But what I did was a basic cross-correlation exercise with a 50-meter gap to derive this model of vertical P-wave velocity. When we put that in the context of the glacier, then for the majority of the ice thickness, it looks that the seismic energy is travelling at 3,750 meters per second. But then at something like 900 meters, there's a step up to faster velocities, which may well coincide with the location of this developed ice fabric. And certainly that's really consistent with observations from surface seismic data in the similar area. We also noticed that in the very bottom of the glacier, the velocities are slower, and maybe that's indicative of temperate ice, this warm ice where we've got liquid water within the crystal, between ice crystals. However, let's take a look at those frequencies again. The three spectra that I've plotted correspond to depths of 50, 500 and 800 meters, and the dominant frequency in the seismic data is always around 200 hertz. So it's a nice high frequency source, and I thought that we'd be able to measure quality factor, get some indication from on glacial temperatures from spectral ratios of these arrivals. But the frequency content really doesn't change very much, and that's a little bit surprising. What I was able to do at least was to look at the amplitude of the seismic energy. So this was after correction for geometrical spreading. So all we've got is kind of the amplitude decay that can't be explained by geometric processes. And you can see there's a nice linear reduction in amplitude with depth. And then there's a big kink at around the 900 meter mark. And again, I think that this is related to the less efficient propagation through the warm ice. But it would be nice to be able to put some Q values on this, but I'm concerned by the lack of change in those spectra. So I'm curious about this frequency behaviour. The first question is, should there even be a measurable frequency shift in these data? What I've done is enlarged the spectra just here, and you can see that, noise aside, all of these spectra share the same dominant frequency at around 200 Hertz. What I did was to take a Ricker wavelet and to propagate that Ricker wavelet through a representative ice model. So it's got a dominant frequency of 200 Hertz. It propagates for 1,000 meters at 3,750 meters per second through material with a Q of 300, similar to what we should expect for ice. And I'm showing the spectra of those wavelets here. So in blue is the unattenuated wavelet, in green is the attenuated one. And you can see that indeed there should be some detectable frequency shift. The dominant frequency goes from 200 Hertz to 170 Hertz. So even though ice is an efficient propagator of seismic energy, for a Q of 300, we still should expect to see some frequency change. So what's going on? So what I think explains these observations is an interplay between the frequency and wavelength components in the seismic data and the gauge length in the interrogator. And this is a concept that I wish I'd known more about at the time of designing the survey, but I didn't. And as it happens, we either got really lucky or really unlucky, depending on which way you look at it, and I'll leave you to decide. But as I now know, the seismic response is derived using the average strain within a given gauge length of a cable. So if we take a seismic wavelet arriving at the cable, if it turns out that its wavelength is the same as the gauge length, because we're averaging, we'll cancel the peaks and the troughs and we'll end up with zero response. So in that sense, the DAS cable has some wavelength filtering characteristics. The practical implication of that then is that the gauge length should be less than 1/2 of your shortest expected wavelength component, and it also means that only wavelength components longer than 2 times the gauge length will be faithfully recorded. So how does that stack up for our particular survey? What we had was a system with a gauge length of 10 meters, which means that there's probably going to be some cancellation for any wavelength components shorter than 20 meters. So what we saw was wavelets with a 200 Hz dominant frequency. They're propagating at 3,800 meters, and that means that the dominant wavelength is 19 meters. So we could probably expect that we are doing some damage to the high frequency components in our data. Maybe that's why our spectra look as consistent with depth as they are, and why our Q analysis is really rather limited. If anyone out there knows of any ways to try and reconstruct some of those amplitudes beyond simply a bit of scaling, then I'd be interested to find out. But I wouldn't be surprised if that means that those high frequency components are unrecoverable. So what went wrong? I think during the early stages of the acquisition design, a lot of the geophysicists involved in the discussion are more used to using other seismic sources on ice than a hammer and plate source. For example, the RV use a vibrator truck in Antarctica, the British Antarctic Survey use explosive seismic surveys, and the dominant frequencies you get from these are probably a bit more like your typical industrial seismic surveys. A hammer and plate source does radiate higher frequency energy, and therefore, with hindsight, an interrogator with a 3-meter gauge length could have been a better choice for us. Now that said, it was still a great experiment. The velocity information that we got out were really useful. Elsewhere in the data from the offset shots, we see both P and S arrivals. We see reflections from the glacier bed and some of the subglacial sediment. So I'm still really pleased with the data that we got. It's just maybe a little limited in the degree of Q analysis that we can do. So just to wrap up, I think we've showed that there's enormous potential for DAS methods within glaciology. We got a large and very comprehensive data set that's still being analysed as we speak, and I think all round we did a very successful demonstration of the method. However, we also did a very good demonstration of what happens when you don't quite get your basic survey design right, and I just wish I'd been more heavily involved in the early stages of planning to sort of facilitate some of those discussions. Communication is definitely key. Now with that, I'd just like to thank first all of the project team involved with this analysis. It's the Responder project, which is funded by the European Research Council, involving academics from the Scott Polar Research Institute, from Aberystwyth University, myself at Leeds, and of course Selixa. A big thanks to them for providing the advice, the systems and the personnel in the field. I'll also say thanks to you for watching this presentation, and if you've got any questions, comments or advice on how to reconstruct the high frequency content, then please do email me, or you can tweet me as well. Hope to hear from you soon. Have a great workshop, and yeah, stay well.